Good morning, class. Today we are going to discuss about the least squares problems and regression analysis. A system of equations may be unsolvable. Although it has no solution, we can always find an x, such that x is being closest to an actual solution. What does that mean by being closest to an actual solution? That means that the difference between ax and b is going to be minimized. So this is actually an optimization problem. When we say the difference is minimized, we mean the distance between the two vectors is minimized, right? And that's the whole idea of the least square problems that we're going to discuss today. In any sciences, you are going to run some experiments to see if there is any relation between the x variable and the y variable. In order to do so, you are going to give x some values, and then you are going to do experiments for each cases here. You are going to get some outcome. Those are going to be y1, y2, and y3. Then you plot them out in the same coordinate system. There is for sure no line would fit the data that you have, right? If you draw a line, it cannot go past through all 3 points. However, for some reason, you still want to describe your data as a trend line, right? The line that represents the trend of the data. The question naturally will appear in your mind. Will you be able to find a line that is closest to all points? Anyway, if you are able to find a line, then you will be able to write it as ax plus b. So we plug in y1 and x1, plug in y2 and x2, plug in y3 and x3. It's almost for sure you won't be able to find a and b that satisfy the exact equalities here. This system would be rewritten as x11, x21, x31, a and b equal to y1, y2, and y3. And so if you denote this matrix as A, denote the matrix of the unknowns as capital X, and denote the matrix of three coefficients, the y coefficients, as B, then you have Ax equals B, which is exactly this equation. This system will have no solution. However, you still want to find something that is closest to being the solution. All right. Now that you have the idea of what we are trying to do, let me go into details. So first is the definition. A vector is perpendicular to a space if it is perpendicular to every vector in that space, and the perpendicularity is expressed as the dot product being 0 for all y in W. Next, the proposition. Let W be a subspace of Rn and X be a vector in Rn. This vector can be in W, may well not be in W. Then there exists a unique vector y in W such that x minus y is perpendicular to W. This vector y is called the orthogonal projection of x onto W. The y is actually called the projection of x onto W. The vector x minus y is called a complementary vector for x that is perpendicular to the whole W. And because it is perpendicular to the whole W, we write this notation. And as you can see, this is just a shorthand for orthogonal. So if you subtract a vector x with its projection on a space, what's left is the orthogonal part that you have. So we are going to prove this proposition. There are two things to prove. You need to prove that the vector y that you can find is inside W. And you also need to prove that x minus y is perpendicular to W. So first we observe that W is a subspace of Rn. So we can find an orthogonal basis for W, say P1, P2, dot Pk, right? Where k is less than or equals to n. Now, if you have a vector perpendicular to W, that means by definition, this vector would be perpendicular to every single vector in W. And so this vector has to be perpendicular to every specific vectors here. And this is equivalent with writing x minus y dot pi is equals to 0 for all I. And this is equivalent with having y dot pi equals x dot pi for all I. By theorem 6.4, if y is in W and W has an orthogonal basis P1 dot Pk, then y would be able to be expressed as y1 prime times P1 scalarly plus y2 prime times P2 plus dot plus yk prime times Pk. And this is the important part of 6.4. This means we have found the y as the following formula. You know that y dot pi is going to be the same as x dot pi. So even if you start with another z with the same properties, then you run the same arguments here, right, using the same basis here, you are going to end up having z being expressed exactly the same as the way we express the y in terms of that basis. So the z and the y are actually equal to each other. So even if you change the basis, then you can compute y with respect to the new basis and the z with respect to the new basis, and they end up being the same with that choice of basis. You will be able to always be able to write y equals z, right? So with this way of expressing the y in terms of the x and the basis here, we know that the y is uniquely determined. And this is actually the projection of the vector x onto the space W. The next proposition says that a vector is perpendicular to a column space of a matrix A if and only if the transpose of A multiplied with the vector x, matrix multiplication here, is 0. In other words, if you want to find a vector x that is perpendicular to a space that is spanned by some column vectors, the columns of A, then you got to solve the system of equation in which the matrix of coefficient is the transpose of the A, and you solve that equation or system of equation to get the x vector here. Theorem 6.20. A be an m by n matrix and B is a vector in Rm, then although the equation Ax equals B may have no exact solution, However, if you apply the transpose of A onto both sides of the original equation, you end up having a new equation, and this new equation always generates at least one solution for you. Furthermore, this solution from the new equation, although it is not the exact solution of the original equation, this solution of the new equation is going to be closest to being the solution of the original equation. In other words, Ax and B, their difference is going to be minimized. So for example, just change these values into some specific numbers here. So then the matrix A is going to be, you multiply the vector x, and you would want it to be equal to the y values, right? There is no exact solution for this one. However, if you multiply with the transpose of A, when you perform the multiplications here, you have 14. and then you have 6, and then you have 6, and then 3. And then you multiply with the x vector, that would equals to, you multiply this and this, you're gonna get 13, and then 6. And so you just find the inverse. And then you multiply it with the right hand side vector, and you are gonna get the A and the B. Very quickly, you're gonna get the A and the B. All right, so you will find the slope A and the y-intercept B. And if you double check this with Excel, ask it to find the trend line for you, you will see that the slope and the y-intersection of the trend line is exactly what you can find by solving this matrix multiplication. All right, so let's prove theorem 6.20. All right, so as explained in the beginning, the idea is AX equals B may have no solution, which is very likely in reality. But we wish to find an X, a vector X, so that AX is closest to B. All right. So this is equivalent with, we want the error, which is the difference between B and AX, to be minimized. So we need to search for an X, so that B minus AX being minimized. Now we observe that when X varies, AX is going to be inside the column space of A, because A is the combinations of n columns. X is a vector of n entries. So if you multiply A and X by the definition of matrix vector multiplication, you multiply the scalar x1, x2, xn to each of the columns of A and then combine them. That means AX is the combinations of the columns of A, so it is in the column space of A. Let's denote this one as W. So in 3 dimensions, we can visualize the W as a plane passing through the origin. We are searching for a vector so that the difference between B and that vector is smallest. And the vector we are searching for is in the column space of A. Intuitively, that should be where you have the orthogonality. Right? So if you want this red one to be smallest, it's got to be this part. When AX equals Y equals the projection of B onto W, which is the column space of A. And this is also true in higher dimension, right? So first of all, by the proposition, let Y being the projection of B onto the column space of A. And so the proposition guarantees the existence and uniqueness of Y, so that B minus Y is perpendicular to the whole column space of A. So this is equivalent with the transpose of A times B minus Y is equals to 0 by proposition 6.5. This is equivalent with A transpose times B equals to A transpose times Y. Now, since Y is in the column space of A, right? Y is the projection of B onto the column space. That means Y is in the column space of A. There must be some x0 in Rn such that y equals a times x0, right? Because being in the column space means that you can write it as the combinations of the columns of A. And this is the same as multiply A with the x1, x2, dot, 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 xn. This is going to serve as your capital X0. And so this result, together with this result, imply the fact that A transpose times B equals A transpose times A x0. And hence, x equals x0 is a solution for the equation ATAX equals ATB. So although AX equals B has no solution, ATAX equals ATB, this new equation always has at least one solution. And that at least one, maybe more. I don't know what are the others, but at least one solution. And that solution is the x0. That happens when we have the orthogonal projection here. This is going to be exactly ax0. And b minus y turns out to be b minus ax0. So we have successfully proven the first part of the theorem, right? The theorem says that we can always find an x satisfy this equation. And we have pointed it out that that should be the x0 here. So the next part, the second part, which is the vital part of theorem 6.20, why should the x that we found from this equation minimize the error for us? So by exercise 6.13, if you have vector x perpendicular to vector y, then you are going to have vector x plus vector y. So you can consider the triangle here. This part is x as well. All right, and so you can see that the square of the length of x plus the square of the length of y is equals to the square of the length of x plus y. Similarly, you also have this, and it's the same as, and this is called the Pythagorean theorem. So b minus ax is going to be the sum of b minus ax0 squared plus the difference between them, right? So this is going to serve like the vector x, and this is going to serve like the vector y, and this is going to serve like the x minus y. How do I know that the two vectors here are perpendicular? Well, that is because you have b minus ax0 being perpendicular to the column space of A. B minus y, but y is ax0, right? So b minus ax0 is perpendicular to the column space of A. What is the y if you simplify here? All right. So if you simplify, it's a x minus x0. Well, if you multiply the matrix A with a vector x minus x0, then that guy is going to be inside the column space of A. And because b minus ax0 is perpendicular to the whole column space of A, it is going to be perpendicular to this vector as well. And because the vector x and the vector y are perpendicular, then they would satisfy the Pythagorean theorem. From here, we are going to have the fact that b minus ax squared is greater than or equal to b minus ax0 squared plus 0, because this part is a square. So this part is greater than or equals to 0. So this implies that the minimum of the error, which is b minus ax squared, is going to be equal to b minus ax0 squared, which happens when ax minus x0 is 0. And so specifically, when x equals x0. Why do I have the word specifically here? I need to warn you that the equation ax minus x0 equals to 0 does not mean x has to be x0. Although x equals x0 is one of the solution you want, but it doesn't mean that this is the only solution you can find. You can find the other x so that ax equals to ax0. And that is when A is deficient, when you have the system Ax equals to 0 has more than one solution. In short, if the columns of A are independent, the only solution is x0. But if the columns of A are linearly dependent, you may have more than one solution. X0 is one of the solutions, but you may still have x1, x2, and x3. Who knows? They will be all considered as the solution for the least square problem. And that at that time, it depends on your choice, your flavor, which one you want to choose. But at least you will have a nice solution x0. And from here, if you look at this, it is actually the square of the error. And in this problem, we obtain the minimum of the square of the error. The square of the error is least. That is why we call the problem the least square problem.